Welcome back, everybody, to another Python tutorial. We're continuing our K-means series. Last video, we were focusing more on removing outliers from our data set, doing some basic transformations, and just getting our data really ready to plot for the most part. That's kind of how we need to think about it. In this video, we're going to be focusing mostly on plotting. I might go to PCA analysis if I feel like it's not going to run too far over, but that's kind of the plan at this point. So first thing we're going to do is we're going to plot our data. So we're going to say matplot, and then we're going to do inline because I want to make sure I can see my charts inside the actual notebook. So we're going to do matplotlib. And then from here, we need to actually import our library. And so we're going to do import matplotlib.pyplot as plot. And then from here, we're going to do some other stuff. So we're going to be doing a 3D chart. And so we got to import some other stuff to allow for a 3D axes. And so we're going to do MPL. Here it is. I'm trying to spell again. Toolkits. mplot 3D import axes 3D. Yes. Okay. Next from here, we're going to define our figure. So define our figure. Pretty straightforward. We'll just create a new variable, call it fig, plot, and then we're going to call our figure object. We've got an axes. Your figure needs an axes. Here, we're going to be doing an axes 3D. Fun stuff. And we're going to pass through our figure object. Now we need to define each axis. So define the x, the y, and the z axes. And so what we're going to do is we're going to do x equals list, because it needs to be a list. It can't be a data frame or anything like that. Nothing fancy as much as we'd like it to be. And then we're going to do iloc. And then I'm going to kind of do that more generic approach. I'm just going to say, hey, that needs to be your first column, because maybe you're going to explore. Maybe you're going to say, hey, I want to do a different attribute the next time, and so on and so on. And then we're going to be leveraging this plot again over and over again. So by all means, like copy and paste to your heart's galore. Okay, from here, we've defined the data that's going to be going there. Now we're going to define the axis labels. So we're going to say axis, define column names. That's going to equal our indicators df.column. So we're just going to call it columns property. That returns a list that we can then set as the axis. So we're going to set the x label to be equal to our column names 0. So some people might ask, like, Alex, why are you doing this? Like, does it really matter? You should always visualize your data when possible. You never know. You might look at it and get like, whoa, there's definitely outliers. That's how I knew there was outliers, because I tried plotting it. I'm like, wait a minute, this ain't going to work. It was pretty obvious. It was apparent. So you should always try to visualize your data. Sometimes there's things that are hidden there that aren't necessarily true, but that's just my opinion. Okay, so we're going to do a scatter plot. So it's going to be a 3-dimensional scatter plot. So we're going to define our x, our y, and our z. And then we're going to do our color. That's noted by the parameter c. I love this royal blue color. That's my color, so don't steal it. I'm just kidding. You can steal it. I'm not going to care. Okay, and so once we define that scatter plot, let's make sure to show it as well, because otherwise, what's the point of plotting it? YouTube's not going to be happy about that. That was not intentional. Okay, what's going on? X, Y, Z. Oh. I feel like I'm rushing now. Okay, perfect. Great. So this is our 3-dimensional scatter plot. You can see here, would that be your X? I think that would be your X. And then your Y, well, yeah, X, Y, Z. So X is the first column, which is return on equity. And then second one is return on assets. So that's your Y, and then return on investment. So at first glance, there actually does seem to kind of be structure here, but I'll be honest, there are some certain things that I'll kind of explain at the end of the video of maybe what we could have done differently. But it's not uncommon to see data kind of like this. And so there's structure here, but it's very clear there's this like dense block down here. I mean, it's very dense. It looks like the majority of our companies, for the most part, kind of live here. And then you've got this kind of outward scatter. And so then these are kind of what I would call, I mean, at least at first glance, the exceptional ones. I mean, they're killing it on return on equity, they're killing it on return on assets, and they're killing it on return on investment. So these are kind of like the rock stars, where these guys down here, they're not that great. they're not doing super good. They're kind of doing poorly pretty much on every measure. And then you got, another bulk right here where it's like, hey, like these are just, they're not bad or good. I mean, most people, hell, 7% return on equity, I mean, it's not necessarily bad, but I guess with the bigger scheme of things, you would say like, yeah, look, I mean, there's a good chunk of companies that are doing relatively well for the most part, you would imagine. So that's why it's important to make sure that you plot your data. Otherwise, it's just it gets messy sometimes. Okay, let's move to the next topic. So I mentioned above that Kmeans is really sensitive to outliers. And so we need to make sure we handle that. Otherwise, it can dramatically impact your results. And so what we're going to be using is inside of sklearn, they have these objects called scalars. And basically what the scalars do is they take your data and they try to normalize it for you. So that way it behaves in a little bit more of a traditional manner. And this is going to come in handy when it comes to the actual modeling component. There's really, there's more than three, but three I'm going to talk about are a standard scalar, a min-max scalar, and then a robust scalar. We're going to find out that we're going to have to use a robust scalar. So with a standard scalar, this is kind of like your z-score a little bit. So basically we take each data point, we subtract the mean, and then we divide it by the standard deviation. The problem is this is sensitive to outliers still, because if you're taking an average of all the data points, it's going to be including the outliers. And so then your mean and your standard deviation are going to be impacted. Same with the min-max scalar. The min-max scalar basically tries to fit all of your data between a range of 0 and 1. Mathematically, what are we doing? Well, we're taking each data point, we subtract the minimum from it, and then we divide it by the difference of the maximum value and the minimum value. Again, this is really sensitive to outliers, because if your maximum value is that 20,000% ROE, you can see how that's going to screw things up. So it's really important that we use the right scalar. So the final one is the robust scalar. This method is a better choice if your data has outliers. With this method, we basically take the interquartile range. So we basically kind of chop off the top and the bottom end, and we use that to be kind of our min and our max in a sense. So it's very similar to the min-max scalar, but we're choosing a very specific minimum and a very specific maximum. We're basically taking it where we're kind of chopping off the beginning and the last part, and then ideally what that's supposed to do is help control for the outliers. So how would that look? Well, I'll do all three examples just so you can see it. They're pretty much identical, but we're only going to be using the robust one going forward. Alrighty. So what we're going to do is we're going to say from sklearn, we're going to do pre-processing, and we're going to do import. Here we go again. Spelling. Min-max scalar, standard scalar, and then robust scalar. There's a jet flying above. It's driving me crazy. Define each scalar. And so from here, we're going to do min-max scalar. And that's going to equal our min-max scalar object. Just like that. And then we're going to have an std scalar. It's probably not a good choice of a name, but whatever. Standard scalar. And then from here, we're going to do our robust scalar. And that's going to equal our robust scalar function. Alrighty, let's scale the data. Okay, so we'll kind of just call it traditional like X-train. So funny thing is, there's not really like a training component of K-means. I mean, some people kind of argue there is, because some people say, well, can be susceptible to overfitting, but we're not going to be covering that in this particular video. Technically, it's kind of hard because like, how do you compare it? Nothing's actually been labeled. So how can you say if it did good or bad? You don't have anything to compare it to. Okay, so indicators, df. Okay, so we call our min-max scalar object and then we do a fit transform. And that's all. And then we pass through our data frame. Okay, so how would, ooh, no, not like that. We're going to do this one and then this one. And then we're going to do standard. And then we're going to do robust. And you'll see, for the most part, I mean, it will change this a little bit, but it's going to keep it relatively the same. And then what we're going to do is it's going to do standard scalar, and then we're going to do our robust scalar. And it's also not really a bad idea to normally kind of what I would say is scale your data. Most time your models do improve when you scale your data. So naturally, that's a really good idea to kind of get into. What we're going to do is we're just going to change a little bit of our component. And all we're going to do is we're just going to say, hey, take that and just take our X train. That's all. Just take our X train robust. Take our X train robust. And then it doesn't need to be a list in this example. It just needs to be our data set. That's all. Super simple. Almost identical. Almost identical. All we did is we took our data and we scaled it. Let's see what that looks like now. Okay. So what you've noticed here, hopefully, is our scaling went down. It's now put it in between this new range of -1 and 2.5, -1 and 4, -1 and 3. So it's scaling the data. It's helping us to control for our outliers and making sure that if there is, it's going to scale it accordingly. So that way it's not going to have this kind of drastic effect on our data set. That's the important part. Remember, Kmeans is very susceptible to outliers. Okay. Let's talk about our next topic, PCA, Principal Component Analysis. Now, I'll be honest, with a 3-attribute data set, this really doesn't justify doing principal component analysis, but I want to make sure that you understand the concept. And so understanding the concept means that we have to visualize it. It's easier to visualize it at a lower dimension than it would be at a higher dimension. I mean, technically you could, but again, I just try to lean more towards on the simplicity part. What's the idea behind principal component analysis? Well, I already mentioned before that some data sets can have thousands of columns, and there's performance implications to that. You know, I mean, that could take a long time to run because K-means isn't necessarily the fastest algorithm. I mean, just algorithms in general. I mean, that's a huge data set. And so sometimes it pays to remove data. But we want to be very specific about which data we remove because basically we want to tell as much of the story as possible with as little information as possible. To give you kind of an analogy, imagine I was telling you a story about a famous dog. So here's one. Clifford is a big... screwed it up already. Clifford is a big red dog with a friendly smile. Okay, so you have an idea of this dog. He's red and friendly smile, everything. Great. Now imagine I added some more details. So I'm adding more information to it. Clifford is a big fire red dog with a friendly smile. You probably went, Alex, that doesn't really make sense to add fire red. I mean, yeah, it gives us a little bit more detail, but we got the general gist of the story without that extra piece of information. Does it really justify adding the fire red? Principal component analysis would basically said, this isn't really adding that much. You really should remove it because you can basically explain like 98% of the story with just this sentence up here. So yes, we do remove information, but the idea is that there's this trade-off. Yeah, I lose some, but what I'm able to gain from it is going to outweigh my loss. That's the important thing to do. And so basically, how does it do that? Well, it uses this explained variance ratio to tell us how much of the variance is explained at any given number of components. And so this is great when it comes to plotting because we can basically use a plot to give us an idea of how many components we need to tell as much information about the story as possible with as little pieces of information as possible. So the components, you can think of it in a sense like the number of attributes. Now, there is some more mathematical concepts behind the scene that you have to understand, but I'm really going to save that for another video. It doesn't justify bringing it into this particular video because you can, in some cases, do an entire tutorial on that concept. So at this point, just understand it's helping us to make our algorithms faster by removing information that's really not contributing that much to the story. So how would we do this? Well, for the most part, it's pretty straightforward. We're going to say from sklearn, decomposition, import PCA. And what we're going to do is we're going to pass through our data set. Well, pass through our scaled data. So we're going to define a PCA, and it's going to be PCA, and then we're going to do fit, and then we're going to do xtrain robust. And so it's going to do all its little transformations behind the scene. I want to plot it. So plot the cumulative summation of the explained and variance. Okay, and so we're going to do plot.figure, and then we're going to do plot.plot, and then we're going to say numpy. Oh, I forgot to import numpy. Import numpy as np, and then we're going to say numpy cumulative sum PCA, and then explained variance ratio underscore at the end. I'm going to put that down a little bit. All right. So now we need to just define the titles and labels. Well, there's really only one title, but you get the point. Plot X label. Okay. So the X label will be the number of components. And then, I mean, you can do a font size if you want. I'll just leave that out for right now. Plot Y label. And then variance, put my little brackets, it's technically a percentage. And then plot title, explained variance. All right. And then we're going to show the plot. So we'll say plot.show. Okay, so what is this telling me? Well, with one component, you can basically explain 98% of the variance. Not much. And then with basically two, that's pretty much 100%. Basically, what it's telling us, you could do it with just one. That kind of makes sense. But in this example, it doesn't make sense to do it. I'll do it for demonstration purposes, but at this point, you're only going to really see this benefit with these larger data sets. So when I do an example in a later series where we have a much larger data set with many attributes, then we'll see kind of the real benefits of the PCA. But really, it's saying it can do this transformation with just two components, and it can tell us almost the entire story, which is awesome. So we only need 2 vice 3. Alrighty, so create a PCA modified data set. And so what we'll do is we'll say PCA data set equals PCA. We got to define the number of components. Well, that comes from our little chart up there. We'll just have it equal 2 at this point, and then we'll do fit xtrain robust, and then we'll do a transform of xtrain robust. So we fit the PCA to the xtrain, and then we transform the xtrain robust data set so that way it's now reflected with PCA information. And then we can store it in a new data frame. Okay, so we'll say PCA data set equals panda data frame, and then we'll do data equals PCA data set, columns equals, it's going to be a list, and then we'll say component 1, and then component 2. And then, do I have any information? I'll just do the head. PCA dataset dot head. Cool. So basically, it's now just reduced down to 2 components that we could then scatter if we wanted. So if we were doing this now and we wanted to do a scatter plot, what would it, look like? Well, let's just do it really quickly, and then we'll call it quits for this video. So plot the figure, and so we'll say plot figure, and what we'll do, define the label and the title. I'm just going to take these guys up here because you know what? For the most part, we just got to change some stuff. Okay. I'm always about that visual component. And then we'll say component 1, component 2. And then we'll say 2 component PCA. And then we got to do the actual plot. And so plot the scatter data. And so we'll say plot.scatter. We'll pass through our PCA data set. And then we'll do, is it lower? No, it's lowercase. Component 1. And then we'll do PCA data set. Component 2. We'll do color equal to royal blue. And then finally, we'll do this equal to 50. I don't know why I did that. Oh, forgot my little bracket at the end. Ugh. Plot, okay. What am I missing? Oh. Okay, perfect. So really, it's still kind of the same structure if you think about it. I mean, if you go up here, not here, here, if you look at that, that looks pretty close to what we're seeing here. It's kind of the same structure. And so we're actually going to see when it comes to the clustering, it's going to kind of tell us the same exact story. But this was more for demonstration purposes. So that way you can see, hey, sometimes we've got too many columns. We need to reduce some. This is how you reduce it. And then this is what it's doing. It's taking that 3-dimensional data set and is basically boiling it down to 2 dimensions. And so that's great. We got less data now that we have to run through our algorithm. But in this situation, with so few attributes, it really isn't necessary. With a 50 column data set or hundreds and hundreds, then yeah, it kind of makes sense. But I've seen some people do 50, 100 columns, no problem. So yeah, you could do it because sometimes it just helps determine if there's this unnecessary data, but it's kind of up to you at that point. But once you kind of start getting over that certain threshold, yeah, it kind of makes a little bit more sense to do it. All right, so that does it for this video. In the next video, we're going to build and run our model. So thanks again for watching, everybody. If you got questions, as always, please make sure to put them down in the comments below, and we will see you in the next video.